Okay, Bismillah ar-Rahman ar-Rahim, wa-salatu wa-salamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, so this is a continuation of still chapter 3, statistical learning, which is like the basis of data science and all future chapters. And we are still in the foundation of predictive modeling in data science. And we continue talking about the generalization risk, and this time with in-sample, the in-sample risk estimation. And I will also introduce the concept of optimism. So we're going to actually review most of the concepts that we have seen before, like bias and variance and overfitting, but just a little bit more formally. So as we already mentioned several times, that our main objective is to have a generalization risk that is as much general as possible. Okay, this is what we want to estimate, because in most of the cases we don't have the exact distribution of data, so we will do that empirically. And this time we will think about doing it without relying too much on the test loss, because the test loss, usually when we have a test loss, a fixed test data set, that will give us only a possible deviation from the estimated risk, generalization risk. We are comparing with only one fixed data set. So that gives only an overview about that. And the test loss can provide an inconsistent risk estimate. Maybe the distribution of data in this particular test data set is not coherent with the other, and that's why it's deviating from the estimated generalization risk. And also, the insufficient data used when limited data is reserved for testing, that means probably this testing data is not representative of the real world. So these are the possible issues that we can get if we rely on the test data set to estimate the accuracy or the generalization risk of a particular model. And the idea here, and you talked about this several times, especially when we talked about cross-validation, is to estimate the in-sample risk. And this means we estimate the risk of a prediction function within a training data set tau. So we're going to train for several types of data from the data set. We're going to take different data sets, and for each data set we are going to compute the average loss, and finally we will average among all of this. And this is kind of empirical estimated generalization risk for the function j, where n is the number of training samples, L is the loss function, and X and Y are the observations. Okay, and the purpose is to provide an estimate on how well the function J performs on the training data when we train it on different types of data sets. And the limitation may not accurately reflect out of the sample risk due to the overfitting and underfitting. So this is a way just to average among all the possible combinations of data within the data set. And this is what we call the in-sample risk estimation. Okay, so basically what do we have? If we know the true generalization risk, and this is possible when we know the exact function J star. For example, if I know the distribution, for example, it is a polynomial function of degree 2 or 3 or 4, so I can compare the deviation between the trained fitting model and the real model. But this is just from academic perspective to assess this. But in reality, we don't have actually the true generalization risk. But I'm going to show you here on a simple example. If we consider a data that is noisy around a particular known model in advance, how we can calculate the optimism. So now we introduce the concept of optimism as the difference between the true generalization risk and the in-sample generalization risk. This is obtained by the training, and this is the true one that we know in advance. And here it tries to measure the tendency for the in-sample risk estimates to underestimate the true out-of-sample generalization risk. It means what is the deviation about the trained loss with respect of the actual loss, or the minimal loss. That's what we want to manage. And the way to avoid this is to do cross validation, as we already mentioned. So how to compare the expected optimism? Okay, it's using the average of the covariance. So don't scared about this, it's pretty much intuitive. So what does the covariance measure? If you have a variable y and a variable x. Salaam alaikum.
Okay.
This is a data science course.
Okay, sorry.
Yeah.
I thought that was the ChatGPT one.
I heard that it was cancelled for today from Dr. Kamal Abu
Okay.
Diya, so I'm not sure about that.
Okay, thank you.
Yeah, you're welcome. Okay, so when you have a variable x and a variable y, and you do the covariance, what does the covariance will calculate? You know what's the covariance? Okay, what is the variance?
Variance is the square root of the standard deviation.
Yeah, what does it mean, the variance itself?
How varied the data
Yeah,
is.
this random variable, how it does variate with respect to the mean.
Yes.
So it's basically the discrepancies or the uncertainty about the values, okay, with respect to the mean, to the population mean or to the sample mean. And the covariance will measure also the deviation of two random variables. How do they deviate with each other? If the covariance is 0, okay, it means they are very much related, two random variables, x and y. And what do we have here? We have the prediction and the real value. We want to calculate the covariance between the prediction and the real value. So if I have high covariance, this means the training loss is optimistic. What does it mean, optimistic? It means it's very close to the training data. Okay, the covariance measures the degree to which the model prediction are in line with the actual outcomes. Okay, and high covariance, it means they are very close to each other. Yani the predicted values are very close to the observed values, to the real values. Okay, if they are very close, and this is for the training data or for the in-sample data, what does it mean? We might have an overfitting because it's very related. They are very related. The covariance between two variables, it measures how much they are related with each other. Okay, the covariance of one value with itself, it's 1.
Yes. Because it's the same value.
Yes. Does this make sense?
Yes.
Okay. So here, the optimism is measured by the covariance, and if the covariance is high, it means it is overly optimistic, and this means that it could lead to overfitting. So this is the summary here. Okay, this is the formula of the expected optimism, which is the covariance between GTXI, the predicted value, and the observed value. And the covariance law, it links the expected optimism to the alignment between the model prediction and actual outcome. High covariance, greater optimism, potential overfitting. Potential, it's not always. Maybe, when do we have overfitting?
High.
When we have low, very low training loss and very high testing loss. So if I have very low training loss, I cannot say that it's an overfitting. I need to look at the testing loss.
Doctor, you mentioned previously that the covariance values are 0 or 1, right?
Yes.
How do we measure that there is a higher covariance?
Yeah, there is an equation for the covariance. Yeah. In statistics. Okay, so this is the proof here. I made the outline of the proof, and this is the calculation on how to prove the expected optimism. And in order to mitigate the optimism or the expected optimism of the overfitting, as I already introduced last time, we use cross-validation. And you have here the k-fold cross-validation. Okay, k-fold, it means how many folds I'm going to use. Last time we presented 5 folds, but we can make it 10 folds depending on how large is our data. And the cross-validation, it's a statistical method to estimate the generalization capability of a predictive model. As already mentioned, we are not going to train on a single data set, training data set, but we are going to have different type of distribution for the training data set to have an overall understanding about the cross-validation loss value, which will be an estimate, an average of all the different loss values that you are going to get over the different distribution of the training data sets. And this is how it looks like, as already introduced. We are going to have, for example, 5 faults, and this is the full set of the training data. We're going to subdivide it into different faults. And for this first fault, we are going to calculate the performance. So the loss here, and then we calculate the loss in the second fault, in the third fault, in the fourth fault, and fifth fault. Finally, we do the average among all these different faults for the loss, for the training loss, and also for the testing loss. And this will represent a good estimate, okay, an estimation of the expected generalization risk. What is this estimation? It will be just the average of all the losses over different type of faults. So we're going to split the data into K faults from C1 to CK. And for each iteration, we are going to train on a particular set of faults, okay? T minus K and test on a CK. Okay, for example, I will take CK for testing and all others for training. And this is what denote as T minus K. It means the whole training minus the kth sample, okay, depending which K it is here. And we calculate the loss, which is L for the fault CK, the test loss. And finally, we can calculate the average, okay, represent the weighted average of the test loss for each fault. Okay, and this represents an estimator of the expected generalization risk based on the testing data set. Now, we don't have only one testing data set, but it's going to vary from one to another, and this will give a better overview. So when later on you will train machine learning model or deep learning models, the good practice is that you divide your data into different faults, okay? So this is part of the general concept. Now, what we are all doing in statistical learning chapter, having this general concept, starting from when we start to work on regression, on classification, on SVM, we are going to apply this concept consistently for training models. So this gives you the needed background, the required background to become a data scientist and to know how to train models. But training model is simple, you know. For every type of model, there are already Python libraries available. You just run them. But now the difference is how to run your model, how to make it successful. The tools are there, but you must know how to use them, how to split your data set, in which ratio, okay? You need to understand your data, the distribution of your data. Don't just, go directly into fitting the model and getting, if you don't do the things in a systematic manner, you may later on need to redo all the things if you are not lucky enough for your model to work as expected. So it's better to work on a systematic manner. Okay. Any question? So now I'm going to take a step back and try to introduce the concept from the very beginning on how to model, okay, on how to do data modeling. This is very important because usually we will start from a problem, general problem, and you want to make a mathematical representation. And what I'm going to present here is something that we have been doing in the previous slides, but this is just to give you a clear roadmap about the mathematical representation. So basically everything in machine learning, we need to reduce the model into a matrix representation, okay, and then try to search for an optimization problem. We need to reduce a certain objective function. It could be a loss function in the case of supervised or non-supervised learning. It can be a reward function in the case of reinforcement learning. And the most important thing is to understand how to model your problem mathematically. And this is very important in statistical learning because it facilitates understand complex systems, and there is no single way on how to mathematically model a particular data problem, and also enables prediction and inference from data. And everything in machine learning is just numbers. Whatever your data is it's images or text or any kind of modality, you need to reduce it to numbers. And these numbers can go from int to very high precision float numbers. Like float 64 is kind of default. Some people can go to float 1.28 because everything is matrix multiplication and precision plays an important role in the accuracy, but of course it will induce much more complexity in computation.
Does the media that we want to train the model in, like if you want to have a picture and turn it into number, will you use decimal numbers more, or will it be integer more? Or
Usually training with integer is not sufficient and it's not accurate, because everything is actually, all the accuracy is in the decimals. And usually, like high precision models, they can get more accurate. You can get more accurate models when you higher precisions. But the problem, you will struggle in terms of memory and in terms of computing, because memory for when you have a float over 128 bits, every number it will take 128. But if you reduce to 32 bits, so you can use this memory for 4 times more data. Okay, so this is how we look at it from computing perspective. This is in terms of memory and also in floating bit operations. It will become much more complex and much heavier to train. So this is why in very large trainings, when we don't have sufficient resources, we may need to reduce the floating point precision to 32 bits or 16 bits, sometimes up to 8 bits floating number, and sometimes they go to even integer. But usually in training we don't go to integer, we train in floating number, but in the inference we do what we call quantization. And one of the technique of quantization is to reduce the precision of the numbers. This is what we call quantization, quantizing the model. In this case, the model is already trained, the architecture is there, the precision will be reduced to some extent just to speed up the operation. So you can, for example, process 20 times faster, and you may lose, for example, 10% of the accuracy. Okay, because in some cases when the model is very complex, but it's very slow, you want to have a prediction in real time. You don't want to wait 5 minutes. For example, if you have license plate detection, you don't wait 1 minute for the door to open if the license plate is recognized. You want to do it in 1 second or 2 seconds. But if your model is very complex, you cannot run it in real time. So usually when we train, we focus on accuracy and reducing the cost. When we go into inference, so we will have different type of optimization requirements, like the real-time execution of the model.
Depends on what we need.
It depends on what we need, yes. So you will try to make the balance between accuracy and also between real-time inference. So inference, it means using the model to make predictions. This is what we call inference. So the first principle here is to model data as vectors. So every input or output, we're going to model it as X. And this is one realization of the training data set. And when you use capital X, it means this is a representation of the whole data set. But this is one realization. I can get a data set of temperature, and I take one realization of this data set to train. So this is what we call as lowercase xi. And in most of the cases, we have unknown probability distribution function. So usually we don't make any assumption. Sometimes you can make an assumption. This is what we call parametric models. Or we can just don't do any assumption, and in this case we will consider non-parametric models. I will talk about this just in a few slides. Another important aspect when you model your data is the assumption that they are independent and identically distributed. Think about it. If there is a data dependency, you cannot rely on prediction, because you don't know, for example, if there is any kind of data dependency in training, you don't know what kind of you cannot model the dependency itself. So we consider that this data is completely independent. They don't have, but this is not really true if we look in the reality, it's not really true. Everything is dependent on something. But whether these things will affect the result or not, that's another story. But this is an assumption. For every kind of representation of data, we consider that, for example, I make image classification, these images are completely independent. In time series, a temperature now is independent from the temperature that will come after. This is not really true, but it's an assumption that will help us do computations, for example, in joint, to calculate the joint density, okay, among all the input variables. It will be just the product of the marginal distributions. Okay, and what is the difference between joint distribution and marginal distribution? For example, if you have, this is a variable. Now, this is the code here. I don't know whether it's clear for you. Okay, let's assume that we generate two random variables, x and y, and basically both they have zero mean, zero average. So this plot here, that shows the distribution of the x value, and this shows the distribution of the y value. So they are independent, and they have identical distribution. Both of them, they were created according to the normal distribution. Okay? And this plot represents the joint distribution of x and y. Okay, this is the distribution. So look now. Here, the distribution of data is around 0. This is just in two-dimensional. This is x1 and this is x2. Look, since x1 and x2 both they have an average in 0, so the concentration of the data is in the middle, 0 and 0. Okay? And of course, as you spread away, and this spreading, it depends on the variance, on the confidence intervals. So this is a representation using the KDE plot in Matplotlib, and in Seaborn also. You can visualize the joint distribution between x1 and x2, two independent variables. They are independent, but they have identical distributions. And look now, if I change the average value from 0 to 3 for x2, now the concentration of point will be around 0 for x1 and 3 for x2. Because here the histogram is also centered around 3. Okay, so this is just to show you the difference between the marginal distribution. Marginal, it means the independent distribution of variables. But of course, this should not represent the same variables, because usually if we say they are identical distribution, both they should have the same distribution with the same mean and the same variance. But this is just to show you, okay, if we have the mean is different, so the joint distribution is going to be different as well. Okay, so of course we have different type of sampling distribution. It can be normal or binomial and exponential. So sometimes when the model is parametric, we can try to assume that, for example, the distribution or the marginal distribution or the joint distribution follows a certain distribution, like normal or binomial or exponential. But in reality, this is not always the case. And this is why in parameter estimation, we have two types of estimation models. We have the parametric and non-parametric. So the parameter estimation, it means we would like to estimate the parameters of a model sampling distribution based on the observed data. And you have two cases. Either you will say, I will make an assumption that it follows a particular model or a particular distribution. For example, you can say this model, most likely it follows a linear regression. So you make an assumption and you are going to optimize the parameter for a linear regression model. Another way to think about the problem, no, you say, I don't make any assumption. I don't know. My data is probably very complex. So I'm not going to assume any specific form of sampling distribution. I will try to discover what's the probability density function. Okay, so we'll try to estimate a probability density function that is unknown in advance. And in the parametric, you'll say, if I assume that is normal distribution, I will try to find the variance and the average. And I will show you some examples. Now for parametric, as already mentioned, the model assumes a specific form for the sampling distribution characterized by some parameters, like the linear regression is characterized by two parameters, beta 0 and beta 1. Polynomial regression, it may be characterized by beta 0 to beta n, depending on how many degree in the polynomial we have. Or we can also assume the parameters of a certain distribution, like the normal distribution. So the advantage of parametric model, they are simple, because usually they have few number of parameters to estimate and simplify the analysis. So we are going to look for a finite number of parameters to model our distribution. And the efficiency, so more data efficient when the model form is correct. In the other way, with the non-parametric model, we don't make any assumption of specific form for the sampling distribution, and we focus on estimating
إلى فتح قفل آيفون أولاً.
And we focus on estimating the distribution directly from the data. So the data is going to discover what kind of distribution we do have. And some of the examples is the kernel density estimation. It means we are going to estimate the probability density function. This is what we call the kernel density estimation. It means estimating the probability density function of a random variable without assuming its shape. So the advantages is that the model can model complex distribution that the parametric model cannot, because we don't make any assumption. And it's adaptable. It's more robust to data variations, okay? Because it will be following the data more than following a particular model. And this is ideal for exploratory data analysis. Look at this example. This will explain you everything. Now imagine we have this distribution of data between income of a student that was graduated, the years of education, and the senior level. Okay, so usually there is, for one person, there should be a relation. When the years of education is higher, the salary tends to be higher, and even becomes higher when it has more senior level. Okay, so these are data, and this is a model for this data. This is the real model for that data. Okay. So how can we now imagine that you would like to develop a model for this one? If we are going now to follow the parametric modeling approach, how we will think? شوفوا الشيء الآن.
We will look for parameters.
Yeah.
And see what we want to measure.
We can make an assumption that there is a linear relationship between income, year of education, between year of education seniority, and between seniority and income. فيقول لي أصبح هذا straight line, and straight line. So I will have like a linear shape, rectangular shape. And this is the case of parametric estimation. I will assume that I will have a multivariate regression. This is what we call multivariate regression. So the estimated value, for example, if I look for the estimated income, it will be a function of x1 and x2, which is the years of education and seniority. And this is going to lead to a shape like this. This is parametric. I fixed the model. It's a linear regression. It's multivariate linear regression. So I'm going to optimize the model to find the optimal values for beta 0, beta 1, and beta 2. And of course, you can have multivariate estimation with more than 2 features. These are only 2 features, just for visualization perspective. And this simplifies the estimation of the function fx or gx by estimating these 3 values, only limited number of values. So we can use the ordinary least square, we're going to have a complete chapter about regression and understand how to do that. That's a common approach to solve this problem. You don't even to train a machine learning model, it's just a numerical approach to solve a linear regression. Okay, it's like solving the problem of multiple equations with unknown variables. You have had this in calculus or in algebra. In linear algebra, yes. So it's pretty much will be reduced to the same thing. Okay, and this will lead us to have a shape that will map between the income, years of education, and seniority. Now, if we don't assume that there is any kind of possible distribution or possible function, in this case we can follow the non-parametric estimation approach, and we try to estimate f as close as possible to the data points. And this will lead to shape something similar to this one or similar to this one. You can see it's more accurate with respect to the original model. But of course, this is much more complex to represent. How to find these parametric values, or these values here, in the example of thin plate spline, in this case, it feeds the data with a flexible surface to capture the complex pattern. Okay? No, this is just an optimization problem to find the distribution, okay, the probability distribution function in three-dimensional space over here. And the key concept here, we use a non-parametric approach, so this offers a flexibility, a wide range. So look now, we have two types of estimation. One that is smooth and another one that is more sharp. Okay, and both of them they provide, okay, this one is more overfitted to the data. This one is probably more simplistic and more general. And later on, of course, we need to calculate the loss, the test loss and the train loss on both to see which one is a better representation by applying all the concepts we've seen in the previous lectures. So the advantage is it can accurately fit more complex models, and this one, it cannot. So if I have more variations here in the data, it will just increase the loss and the discrepancies between the points and the model. The model can adapt, but still not as close as this type of non-parametric estimated model. Yes?
If you know the data will drive you to a certain function, then I can just assume that my data will take me to either a linear function or a
Yeah, we do this when the problems are simple. For example, if you visualize the scatter plot between x and y coordinates and you see like there is a linear trend, you say, okay, most likely I will have. So the assumption that you will do it is probably based on your observation on the data. If you have an observation that can just provide you some hints about what kind of model could fit, yes, in this case you can use a parametric approach. But if your data is very complex and you cannot find a pattern, a clean pattern, it will become more complicated to develop.
That's why uncertainty is always.
Yes, it depends on the uncertainty and the observation of the data of interest. Okay, and the challenge requires a large number of observations because there is a risk of overfitting, of course. Here there is a risk of underfitting. The model is too simplistic. And here the model, it's like in two-dimensional space, we have either one line or polynomial regression. This is like a polynomial regression maybe in three-dimensional space.